course 1210 in first year, you did some geometry of lines and planes and space. But before that, you talked about vectors. That material I wrote coming from sections 11.3 and 11.4 in the present calculus book. I expect you to know all of that material. It contains material about components of vectors, and dot products, and cross products. But there is one difference in notation. In 1210, we were careful to distinguish between two things like this. When I put parentheses around three numbers, that was to indicate that these were the coordinates of a point. If I wanted to talk about vectors, we didn't use the parenthesis notation, we used this angular notation, and we were careful not to mix those up. I wrote the calculus book long before I ever wrote the book or my notes on 1210. As a result, in the calculus book, that distinguishing feature is not made. Calculus book, right? All coordinates of points are indicated this way, and vectors are also indicated this way. It's up to the context to tell you whether you're talking about this being the coordinates of a point ABC or the components of a vector ABC. Context, again, will always make it clear what we're talking about, but we no longer have this special notation that we had last year in 1210 for components of vectors. Do be aware of that. Section 11.5 contains material on lines and planes that you also took in 1210, and I expect you to know all of that. So I think for that material, I'd like to make at least a quick review. Planes. When we talked about planes in 1210, we came to the realization after some discussion that a plane is completely characterized by two things: a vector, ABC, perpendicular or normal to the plane, and a point x1, y1, z1 on the plane. If ABC is a vector normal to the plane, then the equation of the plane is going to have this form. Those three components of the vector perpendicular plane are the numbers sitting in front of the x and y and z. Then there's a d here, and d you can get by substituting these three numbers in for the x and the y and the z, and you determine d. All linear equations describe planes. All planes are described by linear equations. For example, let's do an example. Find the equation of a plane containing the 3 points (1, -2, 3, 4, 0, and 2, and -3 and 2 and 1. I think you will agree, based upon 1210, that 3 points, as long as they're not collinear, will determine a plane. So we made a diagram, even though we probably don't need it. If this is a point, let's call it P, 1, -2, 3. This is the point Q, 4, 0, 2. And this is the point R, -3, 2, and 1. You notice, I didn't care where I put them. I'm not trying to say that this is where P1 should be, because obviously that may not be true, right? This one says it's got a y coordinate equal to 0, and that certainly doesn't look like, and this one says it's got an x coordinate equal to -3, and I'm not sure that that's true, right? That doesn't matter. What I'm trying to do is get a feeling for what's going on. It doesn't have to be an accurate picture. So back here it says what we need is a point on, and we have 3 of them, but we need a vector perpendicular to the plane. So the question is then, how do we come up with a vector that is perpendicular to this plane that contains those 3 points. So if I join like I did there, I make a triangle, and the plane then is that triangle extended in all directions. Again, what we need is a vector perpendicular to the plane. What you did in 1210, you said, well, if I make the vector PR, and I make the vector PQ, and I cross those 2 vectors, I would get a vector perpendicular to both of them, and that would therefore be a vector perpendicular to the plane. So that's how we're going to produce the A, B, and C. We will take the PR vector, and we will cross it with the PQ vector, and it doesn't matter which ones you take. Okay? You take any pair and cross them, and you will get a vector perpendicular to. Remember how you took cross product? You use this determinant notation. IJK across the top, and then the components of PR in here, and the components of PQ in there. To find the components of PR, the vector that goes there, you take the B coordinates of this, and you take those coordinates away, and you get the components of the vector. So -3 minus 1 is -4. 2, take away -2, 4, and 1, take away 3, -2. So those are the components of the PR vector. Similar to the components of the PQ vector, that one minus that one, 3, that one minus that one, 2, and that one minus that one, -1. So take and do that. X component is that one times that one minus that one times that one. That one times that one minus that one times that one looks like it's a 0. The Y component, you take that one times that one, -6, -4, -10, and finally for the Z component, -8, -12, -20. So there is a vector that's going to be perpendicular to this plane. Okay? But I don't have to use that vector. Okay? All I need is any vector. So why don't we take a vector perpendicular plane is anything like that looks like that, any multiple of that. So how we have factor out -10 and say 0, 1, and 2. That's also a vector perpendicular to this plane. An easier one to work with. But if you want to work with the -10 and the -20, be my guest. Therefore, equation of plane has to be in the form that AX is 0, BX is Y, CZ plus D is equal to 0. So that must be the equation of this plane. All we have to do is get the D, and we can use any one of these 3 points to get the D. Why don't we use this one because it's got a 0. Right? So since a point 4, 0, 2 is on plane, if we substitute it in, we get 0 plus 2 times 2 plus D is equal to 0. Therefore, D is equal to -4. And then finally, equation of plane is, put that in here, Y plus 2Z plus D minus 4, put it on the other side, 4. So there's the equation of that plane that contains those 3 points. And you saw that kind of problem last year in 1210 and many others that were like it. Lines. Meaning straight ones. A line in space is characterized by a vector parallel to it and a point on it. So not like a plane, both need a point. Plane needs a vector perpendicular to it. Line needs a vector along it. parallel to it. We saw three forms for equations of a line. And it would have to be equations, right? Based upon 1210 or based upon last day's discussion. If you want to talk about a line, which is a curve, you could talk about it as the intersection of two surfaces. So you would need two. And you talked about three ways to write down equations of a line. First, there was a vector equation, which I'm not particularly interested in because I don't ever seem to use it. But the other two were parametric and symmetric. Parametric being the most important. And they were parametric equations of a line. They took the form x equal, y equal, z equal. There was an x0, a y0, and a z0. There was an AT, a BT, and a CT. What were these? These were or represented a point on line. And these three numbers, vector parallel or on. Vector parallel to line. So once you know a vector parallel to a line, you know a point on it, you can immediately write down parametric equations for the line. But notice how many? Three, not two, as I was suggesting a minute ago. And the reason is because we have this parameter. If A, B, and C are not zero, if A, B, C is not zero, and if you write this meaning none of them can be zero, then you could solve this for t, you could solve this for t, you could solve this for t, and you could equate them, right? If you did that, you get x minus x0 over A, y minus y0 over B, z minus z0 over C. So these ones again were called parametric equations. These ones are called symmetric. For the line. You see why they use the word symmetric? Because each of the three pieces looks the same. How many equations are there? Well, you might say three, but it's really not three. You could say that's an equation, that's an equation, and this one equal to that one, that's the equation, but they're not all independent. This last one of this one equal to this one is a result of those being equal and those being equal. So there really only are two independent equations there, supporting the idea that I need two equations to describe a curve, in this case, a straight line in space. Here there were three because the parameter is there. Notice, if you did this, that's an equation in x and y. It just happens to be void of z. And if x0 and y0 and ab is your constant, then that's a linear equation. So this actually is a plane. So is that. That's the equation of a plane. And these two planes are intersecting in this straight line. So you've got these two surfaces being planes, intersecting in a curve, the curve being a straight line. Exactly the same thing we were talking about last day, but now things are very special. The surfaces are flat, and the curve is straight. An example. Find equations for line parallel to x minus y plus 2z is equal to 3, 4x plus 2y minus z is equal to 6, and through the point 1 minus 2 and 4. First of all, does it make sense? Because what we need for the equations of a line are a point on, yes, I gave you one. 2, you need a vector parallel to it. I didn't give you anything like that. I gave you this and this. What's this? That's a plane. What's this? That's a plane. What are two planes intersecting? Because I put them together. They intersect in a line. Oh, so what I'm saying is, I want equations for the line parallel to this line and through that point. Maybe a picture. So we've got one plane, we've got another plane. Those are the two given planes, that one and this one. And then we got this point down here, 1 of minus 2 and 4. So we want the equations for the line through this guy parallel to that one. So all we have to do is find a vector along this line, and then we can use it to write down either the parametrics or symmetrics as long as A, B, and C are 0. Well, how do we find a vector along this line? What you did in 1210, you said, a vector perpendicular to this plane is 1 minus 1 and 2. 1 minus 1 and 2. The coefficients constitute a vector perpendicular to that plane. If you go to that same point, you can find a vector perpendicular to this plane. It's 4, 2, and minus 1. 4, 2, and minus 1. If you want a vector here along the line, it should be perpendicular to this one and this one. But how do you find a vector perpendicular to others? You cross them, just like in the last example. So, a vector parallel to line is going to be the cross product of those two vectors that we just wrote, those two normal vectors. So we got 4, 2, negative 1, 1, negative 1, and 2. X component, 3, y component, negative 7, and z component, negative 6. So there's a vector along this line. We can now write, we could write these ones, none of the components are 0, but I like these ones. These parametric equations turn out to be far more useful than those symmetric equations. So therefore, equations of line are x equal, y equal, z equal. Down here, point on, give it to 1, negative 2, 4, plus, 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 vector parallel to 3t, minus 7t, and minus 16. So those are parametric equations for the line. Are they unique? There is one and only one equation for a plane. There's an infinite number of possibilities for equations of a line. All you need here is any point whatsoever that's on the line. Didn't have much choice here, that's all that I ever to do. And here, any vector along. So if you want to write a 6, a minus 14, and minus 12, you can do that if you want. If you want to write 3 halves, minus 7 halves, and minus 3, be my guest. All right? They're all parametric equations for that same line. Not unique. So those are ideas that you saw in 1210, along with a bunch of other possibilities for finding equations of lines and planes in space. You need to be able to do that again. That again is material in 11.5. Talks about some geometric applications of vectors that turn out to be very useful. The first thing I want to talk about is the components or component of a vector v in the direction of another vector u. Talk about the vector component of that vector in that direction. So I give you any vector and any vector. So in other words, if I give you a vector, it's got an infinite number of components depending upon the direction you choose for u. Right? You know about x components and y components. Now we want to talk about component in any direction whatsoever. Picture, what we do is we draw the two vectors tail to tail. So there's the vector v, and here's the vector u. I want to talk about the component of this vector in this direction. And that vector u could be in any direction here that you want whatsoever. I seem to be drawing in the plane, but don't get the idea that it has to be plane. This could be in space. What we do is we drop a perpendicular from v down to u. Let the foot of that vector be called r. Let's call this point P that we put the two tails at. We define the component of v in direction v is the directed distance PR in that diagram. So it's the directed distance from here to here. Once you put in the word directed, you're trying to say that it could be positive and it could be negative. And here, in this one, it is positive. If R lies on the same side of P as the tip of U, this PR is positive. But I could have the following scenario. Suppose this is V and this is U again. Now when I drop the perpendicular, I have to do this. This PR is regarded as negative. When the R is on the opposite side of P from the tip of U. So this one is a negative PR. This one is a positive PR. So components can be positive, can be negative, depending upon the orientation of these two vectors. What we want to be able to do is find out what PR is. How much is PR? Well, if I call this angle in here theta, would you agree from this triangle that PR is equal to the length of V times the cosine of theta? That this one over this one is that. This one over this one is the cosine of that angle. So if I knew what theta were, I would be able to calculate PR very quickly. But I don't know what theta is, so what I want to do is I want to get rid of it. The question I want to ask is that true here? If this is now the theta, is that still true? And I'll leave you to think about it. The answer is yes, it is. So it doesn't matter whether you've got the top scenario or the bottom. This is a correct formula for getting that component. Would it be okay if I did the following? If I put right here, hat. What does hat mean? Recall that when you put a hat above a vector, it means that is a unit vector, a vector of length 1. So u hat might be, say, here. That might be u hat, that might be length 1, that much length is got about length 2. You can't argue with that because the length of a unit vector is 1. So I didn't change anything, I could spin it much more complicated. But you will recall from first year that if you wanted to talk about the dot product of two vectors, v dot, maybe I use different letters, I'll say r dot s, and those are two vectors, you get it by taking the length of r, the length of s, times the cosine of the angle between them. That was one way to calculate dot product or scalar product of vectors. But you'll notice that looks exactly what this is. It's got the same form. So as long as theta is the angle between the v and the u hat, and it is, it's the angle between v and u, and that angle doesn't change when you take the u hat, this is nothing more than the dot product of v and u hat. So in other words, to calculate the component of a vector v along a vector u, you simply take the dot product of the v vector with a unit vector along the u vector. Right. So we can take components of any vector in any direction simply by taking dot products. Example maybe? Component B equal 1 minus 2 and 4 in direction U minus 3 minus 2 and 1. All this formula says is you take the dot product of the V is V dot U hat. V is equal to 1, negative 2, and 4. You dot that with a unit vector in this direction. And to find a unit vector in that direction, you simply take it and divide it by its length. Like that vector is the square root of 9 and 4 and 1. So take the dot product, I get minus 3, that we have now gets plus 1, 5 over the square root of 14. So that's a component of the vector v in the direction u. Relatively straightforward. We're going to need that shortly. In a minute, we're going to be talking about distance between various things in space, namely distance between points and lines, points and planes, lines and planes, and lines and lines. And every one of them, well, we use this component idea to do it. So it's important to us. So as I said, I want to talk about distance between points, lines, and planes. Basically, there are 6 of them. Point to point, point to line, point to plane, line to line, line to plane, and plane to plane. Right? I want to be able to calculate distance between any of these. So distances between points, lines, and planes. 1 point to point. Well, there's nothing new here. We did this at section 11.1. They had a formula for the distance between 2 points. Did it in 11.1. 2. Let's talk about point to plane. In all of these distances, you're going to have to ask the question, what kind of distance do you mean? And normally the idea is perpendicular. So let's draw a plane. So here's a plane. And here's a point P, x1, y1, z1. Now that's the equation as plane B. What we're going to do is, not an example, I'm going to generate a formula. I'm going to, instead of working every example you'd ever come across from scratch, we'll do it, put it in general, get a formula. Now you can use this formula from now on. So let's suppose the equation is plane is this. These are the coordinates of the point. We want to talk about the distance from this point to this point. And by that, we would mean the shortest, which also turns out, therefore, to be the perpendicular. So you would drop a perpendicular down to the plane, and say, if I call that R, r, I want to know what the length of p to r is, right? So that is what we want. The length of the vector pr that joins p to r. The problem is, I don't know where r is. I need to find out, well, that's one possibility, is to find out the coordinates of r. And think a minute how you might do that. Could you find the coordinates of that point r, and then we could use the formula point to point? And the answer is yes, you could. But if I do it that way, then I'm going to have to do all problems by the same procedure, and I won't have a formula. The way you could do it is say, I could find parametric equations for this line. Because a vector along it is ABC, and a point on it is this. So I could write down symmetric equations, parametric equations for this line. I could put them together with the plane and find the point of intersection of the plane and the line. And then I'd have the coordinates of r. That you could do. I don't want to. I want to generate a formula so I don't have to keep doing that over and over and over again. So here's what I propose. Suppose that Q x, y, z is any point in this plane. Any point that you want, right? R is a particular point, it's the foot of the perpendicular, but Q is any other point. And suppose I do this. I join this, and I join this. But I'd ask you the following. Is the component of the PQ vector along the PR vector precisely PR? Well, how do you find components of one vector on another? You want the component of this vector along this vector. You drop a perpendicular from here over to there. Is it going to hit R? Yes, it is. All right? So then PR is going to be equal to the component of PQ along PR. Right? But and I know how to do that. I know how to calculate it. You take the PQ vector and you dot it with a unit vector in the direction PR. Now I can find you PQ. I'm giving you P, and I said Q is any point you want that's in the plane, so I can find one, no problem. You give me a equation of the plane, I can find a point satisfying this. If all three are there, I put U to 0, solve for Z, there's one. So it'd be easy for me to find any point in the plane. Well, let's talk about the other one, PR. I don't know what PR is. That was my problem. I don't know what R is, but I don't want it. I want a unit vector along here. A unit vector, PR. Ah! Could I find a unit vector along there without finding R? The answer is yes. A vector along here, it's ABC. So we could say that PR is ABC, that vector, divided by its length, which is the square root of A squared plus B squared plus C squared. How does that look to you? Well, the problem is it's not quite right, because I don't know, is it in the right direction? It's along the right way, but maybe it should be going this, maybe P's down here, so it should be the other way. So let's take and say, if we do this, one of those two is correct. I don't know which one. It depends upon where P is relative to the plane. But it's one of those two. So we can see now then, carrying this, that the PR length, which we said was PQ dot PR hat, is equal to PQ, right, dotted with this plus or minus ABC over the square root of A squared plus B squared plus C squared, right? But we don't know which is the plus or the minus. but you're going to choose the appropriate one so that when you do this, it turns out to be positive. Well, why don't I say, hey, since we want the length of the vector, we can make sure that happens if we put some absolute values here. That will guarantee that it's positive. So we won't have to worry about choosing the right one. The absolute values will take care of it for us. Well, now we're getting there. All we have to do is think about the PQ. PQ was this vector here. Well, let's take a look at that. PQ is from P to Q is x minus x1, y minus y1, z minus z1. That's him. Dotted with plus or minus, but we can drop the plus or minus now, because that's being taken care of by the absolute values over the square root of a squared, b squared, and c squared. There! Well, I could pull the square root way out front, right? Pull that square root way out front. 1 over the square root of a squared, b squared, c squared. Absolute value, what's left? What's left is this one dotted with that one. We know how to take the dot product. You multiply the x components, the y components, the z components, and you add. You'll have then ax minus ax1 plus bx minus bx, not b, that's y, y minus by1, cz minus cz1. There. But let's take a look. This one, and that one. That should not be a comma. That's a plus. How much? It's ax plus by plus bz. Remember what q is. X and y and z are the coordinates of the point Q, and the point Q is on the plane. Therefore, these three guys satisfy that equation. And therefore, instead of ax and by and cz, I could put in a minus d. So I could write then 1 over the square root of a squared, b squared, and c squared. The absolute value minus ax1, minus by1, minus cz1, minus d. And why do we throw away all minus signs? And write absolute value ax1, by1, cz1, plus d over the square root of a squared, b squared, and c squared. Now I've got it. I've got me a formula for the distance from any point x1, y1, z1 to any plane ax plus by plus cz plus d equals 0. There's my formula. Memorize it. I would recommend that you do. If you don't, then you will go through this every example that I give you. I think it would be recommended that you memorize that formula. Example, let's do a nice simple example. Distance from point 1 minus 2, 4 to the plane 3x, 4y minus z is equal to 6. Right. You got a formula. That's it. Distance is the absolute value. You take the equation of the plane, but remember that d, you need to take this guy and put it on that side. So I take 3, put in 1 for the x coordinate, plus 4, put in minus 2, plus or minus, and put in z, 4, minus 6, over the square root of 9, 16, and 1. So what do we get? 3, take away those, that makes 10, 18. So does that make minus 15 in here? So 15 over the square root of 26 is the distance from that point to that plane. Right? So there's our number 2. We have point to point. Now we got point to plane. Point to line is a little more difficult, so I'll delay that one for a minute. Do other ones that are easier first. So number 3. Let's talk plane to plane. Distance between two planes. What would that automatically assume? I think it assumes it's a parallel. Because if they're not parallel, they're going to intersect, and then there's no distance, or you can say the distance between them is 0. So this would mean parallel. So if we do picture, we have, there's a plane, and here's another plane that's parallel to it. Then we want the distance between those two planes. Think for a second, and I think you can decide quite quickly how to handle it. What would you know about these two planes? If they're parallel, what would you know about their equations? Would you agree that if they're parallel, then their normals are parallel? And therefore, when you write down one of the equations, this is one of the equations, then what does the equation this one have to be? It has to have exactly the same thing, but it could have a different d. But the a and the b and the c would have to be the same. So we can say this one's d1, and this one is ax, by, cz, plus d2 is equal to 0. That's what they'd have to look like. No. Okay? Now, the a, b, and c here don't have to be the a, c, and d here. Like this might be 1, 1, 1. This one could be 2, 2, 2. Right? They're still parallel. Right? So they don't have to be exactly the same, but you could make them the same if you wanted, because they are parallel. Would you agree that what you could do here is pick a point here, pick a point, in one plane, and find its distance? To the other plane. So there's really not a heck of a lot that's new here. Right? Just pick a point on one plane, find the distance to the other plane, use the formula we developed over at the far mark. So plane to plane parallel, not a problem. Line to plane. Number 4. Line to plane. Distance from a line to a plane. Think about that for a second. Would there be any assumption that you would be making in order for that existence, or that distance to be real? Would not that have to be the same as it was in the last one? The line would have to be parallel to the plane. If it's not, then the line is going to intersect the plane, and then the distance is 0. Right? So this would assume then, again, that they are parallel. Right? So you'd have to say, here's a line, and here's a plane. And the plane and the line are parallel. Otherwise, the distance is 0. How are you going to handle this one? Okay, we do the same thing. Pick a point on the line and take the distance from the point to the plane. Right? So pick a point. Pick a point on a line and find distance from it to the plane. Right. So there's really nothing new here again. Example. What an example here. line distance. Between this x equal 3 minus t, y is equal to 4 plus 2t, z is equal to minus 3 plus t, and x plus 2y minus 3z is equal to 6. And I think we're going to have to agree that this is a line. These are parametric ways for a line, and this is an equation for a plane. So we are talking this scenario. But if somebody gave you that, you have to ask the question first, are they parallel? If they're not parallel, then the distance is 0. So don't go and do this, right? Unless you first of all check whether they're parallel. So we need to check whether this line and this plane are parallel. Question is, how are you going to do that? And I can think of 2 ways to do that. Can you come up with them? Well, I think perhaps the easiest way would be to say, why don't we find out whether the line intersects the plane? Is there a point on the line that's also in the plane? Do they intersect? In which case the answer will be 0 from the required distance. How would you decide whether this line intersects this plane? I think what I would do is I would pick that one up and put it here. I would pick that up and put it here. I would put that one in here, and I'd say, if I can solve for t, then they're going to intersect. If I can't solve for t, then they don't intersect. So let's try that. So we're checking to see if parallel. We're saying method 1, because I want to suggest another method in a moment. Method 1. What we're going to do is put this in the 3 minus t in for the x. I'm going to put in the 4 plus 2t for the y. And then I'm going to put in the z minus 3 plus t equal to 6. I'm going to say, if I can solve this for t, then I have proved that they intersect, and the point would be, take that t, put it here, put it here, put it here, you would have the point of intersection. If I cannot solve this for t, then it's saying they do not intersect. And you will note if you look at the t's, there's 4t, there's minus t, and there's minus 3t's. They all go away. All right? They all go away. Now, what's left? It's important what's left, because if everything else cancel, what would you conclude? If all the numbers now cancel, you'd be getting 0 equals 0. What would that mean? That would mean this line lies completely inside the plane. Which would be a fluke, but that could happen, right? But they don't cancel. Agree? You got a 9 here, you got a 17, you got a 20, and 20 is not equal to 6. Therefore, no solution for t. Therefore, line parallel to plane. That's perhaps easiest way to check to see if they're parallel. I would suggest that there's another method. Method 2. Can you think, a few seconds, see if you can think of another method to decide whether this plane and line are parallel. Here's the idea. could you find me a vector along this line? Call it V. The answer is yes. The numbers in front of the t constitute a vector along or parallel to. So such a vector is -1 and 2 and 1. You could find me a vector perpendicular to the plane. Call that n for normal. Lots of numbers in front of the x and the y and the z. Numbers 1, 2, -3. Would you agree that the line is parallel to the plane if these two vectors are perpendicular? And how do you test for perpendicular? You take the dot product, v dot n hat. All right, so let's start this over here. Vector along line is v equal -1, 2, and 1. Vector perpendicular to plane is n for perpendicular. What do we say? 1, 2, -3. Right? What is v dot n? I take the dot product, I get -1 times 1, I get a 2 times 2, and I get 1 times -3. What do I get? 0. Therefore, line parallel to plane. So we proved in 2 different ways that it makes sense to ask for the distance between this line and this plane. They're parallel. And how do we do it? We said what we would do is we would take a point on the line and use the formula that disappeared from point to plane. All I need is a point on the line. Give me one. Since you say, if I put in here t is equal to 0, I get a point on the line. 3, 4, -3. 3, 4, -3. 3, 4, -3. You don't have to put in t equal to 0. If you want to put in t equal to 51, be my guest. You're going to eventually get the same answer, but who wants to put in here 51 when you can put in 0? So since that is point on line, therefore, distance between line and plane is absolute value of over square root of. On the bottom goes the coefficients in the plane. 1, 2, and 3, 1, and 4, and 9. The top, what do we do? There's no absolute value on the whole thing. Just around the top. So you put that point into the equation of the plane, but remember, make sure you put this guy over here. So x, which is 3 plus 2, the y, which is 4, minus 3, with a -3, -6. So I got 3 and 11, 11 and 9 are 20, take away 6, 14 over the square root of, coincidentally 14, so the square root of 14 is the distance from the line to the plane. Right. So I still have a couple more to go, but that'll have to wait for the next lecture.